Hello students, in this video we'll see how to find the coefficient estimates for the betas in multiple linear regression. Recall the situation in multiple linear regression. Our model is that a vector y is equal to a data vector x with some parameters beta and then a random error. And so here the random error, epsilon 1 through epsilon n, are all normally distributed with mean 0 and variance sigma squared. So here each epsilon I is normally distributed with mean 0 and variance sigma squared, and each of them is independent and all independent. Okay. And so now what we'd like to do is we note from this that the expected value of this vector, y, is just going to be the x beta. That is not random, that's systematic. And so that's one thing we're going to keep in the back of our minds, that the expected value of this vector is x beta. And now the question is how do we find an estimate for beta? So question, how do we estimate beta? And the answer is we look at the sum of square errors. So we want to minimize. We will minimize the error sum of squares. Okay. And so what that amounts to is that saying that if we recall from calculus that the norm of a vector v is equal to the square root of the sum of its components, v1 squared plus vn squared, then what we're really after doing is our goal now is to minimize. We're going to minimize y minus x b. And we can put a squared here if we want. We want to minimize this quantity here, or just square it over all values of b. Okay? And so now what we can do is we can use linear algebra to solve this problem. So we can recall that if y is in the column space of the vector x, then we can solve this explicitly. Then we just find the vector that's in the column space that solves this. But y may not be in the column space. So a note is that y may not be in the column space of the matrix X. So the solution to this problem is we're going to look at the orthogonal projection of y, of this y vector, onto the column space of X. Okay? So if we claim that, consider a y hat, and what is this y hat? Y hat is the projection, this is orthogonal projection, onto the column space of X of y. Okay? And now what we'll do is if that's what y hat is, then there has to exist, then there is a b tilde such that x of b tilde is equal to what? Such that x of b tilde is equal to y hat. Okay? And I claim that this b tilde is going to be our least squares estimator. So this would be our least squares estimator. So now, how do we see this? Well, we know by properties of the orthogonal projection that y hat minus, so y minus x b tilde is perpendicular to the column space of X. Okay? And so what that tells me is that if I hit this with the transpose, then X transpose of y minus x b tilde is going to be the 0 vector. So that's going to be the vector, of course. It's going to be 0. And so the 0 scalar. And so what we have now is we have that x transpose vector y minus x transpose x b tilde is equal to 0. And what this gives us is if we rearrange this, this says that x transpose x B tilde is equal to X transpose of Y. And now, if this matrix is invertible, we can conclude, if it's invertible, that B tilde is X transpose X inverse X transpose Y, and then these are our least squares estimates. The final thing to note is that this orthogonal projection over here, so we know that the orthogonal projection is the point that minimizes this distance. So the orthogonal projection is exactly by definition, the orthogonal projection minimizes this length over here. And so that tells us that this representation, B tilde, is the least squares estimate for multiple linear regression. Thank you very much.